Bismillah ar-Rahman ar-Rahim. Welcome to our second lecture in our formation evaluation course. The previous lecture we covered an introduction to oil industry. We went through drilling equipment, conventional and unconventional reservoirs, and drill rig components and type of drill rigs onshore and offshore, and we stopped in mud logging and drilling fluids. Today we'll continue in our classes, and we'll start with mud logging and drilling fluids. We have talked about it in previous years, but today we will go in more details in its applications. The best way to describe mud logging is by call it the heart of drilling operation, and in the same way that the heart is one of the main components of the human body and play a major role in keeping us alive, pumping blood through our veins to all other body parts. The same way drilling fluids goes through all its the drilling operation, and it's the one that keep the drilling operation alive. The history of drilling fluids started on 1844, and it was using water. In 1864 they start pumping water through the hollow pipe, and in 1890s start using clays, and by 1926 was the introduction of using barite, and since 1934 to 1936 crude oil was added to the mud to reduce the stacking of the pipe. So it has been developing since then, and it's keep developing till now. We will see in a while that recently it's using polymers as an adjective into the drilling fluids. So we have the classification of and composition. In terms of classification and composition, we have different type of drilling fluids. We have water-based mud, and we have oil-based, we have pneumatic fluids. And the composition of the drilling fluid is differ according to the function that it will play in the drilling. So as we said earlier, the choice of the type of a drilling fluid, it has to be done carefully in a way that it will not affect our drilling operation or any other stage in drilling operation. And if you remember, we give an example that, for example, using oil-based mud in a logging operation in which we are using resistivity, for example, oil-based mud will affect that logging operation, because one of the main factors in resistivity logging is that the drill fluid has to be conductive, and oil-based fluid is non-conductive. So such condition has to be put in consideration while choosing the drilling fluid. So the main components, we might have gas, we have drilling solids from the formation, we have gas from the formation, we have hydrate clays, free water, we have bond water, surrounding the clays, and many other components in the drill fluids. The oil-based mud, in it's which we have the continuous phase, which is the oil, and water as a disparate phase. So they are mixed together, and sometimes the oil base can be diesel, kerosene, fuel oil, or crude oil. The advantage of using oil-based mud is high drilling rate, and it also improves the lubrication of the drill bit and drill rig components, and maintaining formation at high temperature. So it can maintain the temperature of high formation temperature. The disadvantage is that it's very toxic, can affect the drilling teams, and it have a very high density and pressure that might cause formation damage, and that is one of the things that is normally being avoided in drilling operation, and contaminate the freshwater areas or aquifers in the drill rig or in the rig interval, which contain fresh water. Disposal of the cutting in an appropriate place can cause huge environmental issues, since it contains material that is harmful to the environment, and the disposal of those cutting in an appropriate way can cause those environmental hazards. On the other hand, the water-based mud, in which the continuous phase is the water, and it can contain clay and other chemicals as a disparate phase. And so normally it's look like chocolate milk, and for those who have been in water drilling rigs, they must be seeing this type of fluid, which called bentonite. It's similar in shape. The advantages: the use of hydrocarbon, because it doesn't contain any hydrocarbon that reduce the environmental effects. You can easily control the viscosity since during the drilling operation you are continuously monitoring the changes in the borehole condition, and according to that you can easily change the composition and the properties of the drilling fluid accordingly. Density also can be controlled from low pressure formation because once you are drilling in high pressure formation, is not the same as drilling in low pressure formation, and you have to maintain a balance between the drilling fluid and the formation pressure all the time. Drill tip is removed from the fluid at the shaker. You can easily wash out those drilling fluids from the cutting sample in order to describe it and study it. The disadvantages is are not as efficient in lubrication as the oil-based mud, can promote corrosion to drill bits because it contains water, and as we know, the drill bit is made of iron and metal, so that can cause a corrosion to the drill bit. It's not efficient at higher temperature. It cannot maintain high pressure formation temperature, and does not carry drill tip to the surface efficiently as an oil-based mud, because Density and viscosity plays a major role in carrying the drill chip from the bottom hole to the surface, and inefficient transferring of drill chips from the bottom of the hole to the surface can reduce the rate of penetration, and because those cuttings will be accumulated at the bottom of the borehole, which is preventing drill bit from penetrating the formation. So we have this question: what's the meaning of the kick? So we will answer this question in a while, and in the previous slides. Now we come to the functions of drill fluids. We have a lot of functions for drilling fluids. We know that the main function is to control the formation of pressure and prevent fluid to flow from the formation into the borehole. Only in very rare case, in which as we will see in coming slides, that there is some cases in which we prefer to allow fluid to flow from the formation into the borehole. Efficiency of transport cutting to the surface, and because those cutting that be analyzed in the surface has to be correlated to the depth from which it's coming. So any lag or delay in the transportation of the cutting to the surface, it can lead to wrong interpretation of the formation. Suspend and release cutting. Those cutting has to be able to suspend through this drilling fluid. Maintain wellbore stability. One of the main issues in the drilling operation is to maintain the wellbore stability and prevent collapse and swelling of formation. Seal permeable formation. We will go in details in this in the coming slides. Minimize formation damage. Cool and lubricate bit. Provide buoyancy for drill string, and transmit hydraulic energy to the tools and the bit. Minimize impact on the environment. Facilitate the retrieval of information from the wellbore, and we will see also this when we talk about directional drilling and measurement while drilling. Control corrosion and maximize penetration rate. This image will show also explain those functions in which place exactly it's happening. So suspend and release cutting, as we said earlier, that those cutting materials has to be transported to the surface in order to be analyzed and studied and described, to give an indicator of the penetrated formation or the succession of the formation throughout the borehole. So the accumulation of those, if the circulation of the drill fluid stop, those cutting will be accumulated at the bottom of the borehole, which will prevent the drill bit from further penetration and further drilling, which will stop the drill operation and cause a loss of time, and of course increase the cost of the drilling operation in all. control formation pressure in two different aspects. So the drilling fluids has to be able to prevent formation fluids to flow from the formation into the borehole to prevent kicks and blowout. And now these kicks are actually the flow of the fluids from the formation into the borehole, and this has to be prevented during the drilling operation. Only in very small cases, which as I told you earlier, and we will talk about it in the coming slides. And at the same time, the drill fluid should not be under higher pressure that it cause formation damage and induce fractures into the formation that lead to loss of circulation. So the drill fluid will be lost through the fractures in the formation. So that's why we have what is called mud weight window. It's a specific range of mud weight pressure that should be maintained in order to prevent those two scenarios to happen. Should be above the formation pressure to prevent kicks and blowouts, and at the same time to be less than the fracture, less than the pressure that can cause the fractures in the formation and cause loss of circulation. Poor and very good bridging. Bridging is accumulation of solid particles in the formation. So or the preventing of accumulation of solid particle in the formation, because if those solid particles from the drill fluids accumulate in the formation, that will block the pore spaces and will reduce the permeability and will affect the production operation. So you will need to deal with those material which is accumulating the pore spaces later. So the bridging is the good bridging is to cover to prevent those particles from accumulating and flowing into the pore spaces. And this is actually an example of the borehole wall. So this is a good bridging and this is a bad bridging. Sealing a permeable formation. As we saw on our previous lecture in the video, that the drilling fluid is actually flowing within the drill pipe and goes out through the drill bit and then travel upward with the cuttings in the annulus between the borehole wall and the drill string. And this circulation is continuous. As we said, the same drilling fluid will go and accumulate in the shell shaker, where it's separated from the cutting samples, and then it goes to a shell container and then to the drill pump and then comes back again to the borehole. Now we talked about the invasion process, and we said it's the process in which the formation fluids went through the formation in permeable zone, and it's as we said, it's mostly happening in the zones where the formation is permeable. So we indicate that this specific zone is permeable by the development of or the formation of the mud cake. So, and as we said previously in briefing, this drilling fluid has to prevent for the drilling fluid from going deeper and deeper in the formation or the permeable formation, because as we see in this image, as those fluids goes to the inside the formation, that will lead to accumulation of more solid particles and formation of a very thick mud cake in the borehole that can cause a stacking of the drill string in the borehole. So thickness of the filter cake or the mud cake, it has to be very low in order to prevent the further penetration of the drilling fluid, and to prevent the stuck of the drill string in the borehole. Now the factor that affecting the hole clean, which is the transportation of the cutting samples from the bottom of the borehole to the surface. It's the annular velocity, the slip velocity, the viscosity, and the density. So the annular velocity depends on the pumping rate. So there is two factors which are actually acting opposite to each other: the annular velocity and the slip velocity. So the slip velocity is the velocity that causes those particles to sink downward to the drill hole, and the annular velocity is the velocity that transport those particles upward, and it depends on the pumping rate. So as we increase the pumping rate, we increase the annular velocity, and we are reducing the sink velocity. This is the description of the slip velocity, and slip velocity depends on the size of the cutting. As the size of the cutting increase, the slip velocity will increase. As the density increase, also the slip velocity will decrease. The shape of the cutting, if it's flat, it will have low slip velocity. If it's angular, it will sink easier. Flow properties of the fluid, which is related to its density and its viscosity. Density and viscosity, this is a conversion between water and honey. So in terms of density and viscosity, water is less in terms of density and viscosity than honey. So the drill fluid has to be viscous and have a higher density in order to allow those cutting sample to be able to suspend in this fluid. So if we put a rock sample in water, it will easily sink. But if we put the same rock sample in a honey, it will, to some extent, it will be able to flow or suspend in this fluid. So the density and the viscosity of the drill fluid is a very, very important factor. Limitation of mud logging. So mud logging is the operation of studying and analyzing those cutting samples, and the information that are collected from those samples are actually presented in what is called master log, as we will see in the coming slide. So those samples are actually, as we said, each sample has to be referenced to a specific depth. So the accuracy of, because it takes too much time to travel from the time it has been cut it by the drill bit and transported to the surface, which is called the lag time. So this lag time, more or less, there must be some inaccuracy in the depth. So the accuracy is up to 5 meters. So that's mean the sample that is described in the master log can be up to 5 meter depth from the depth that it has been described. So the error in this is 5 meters. Rock fragments from various depths are mixed, and this can actually happen because even within the movement of the drilling fluids from the bottom to the surface, it can take some samples from various intervals, and they can be referenced to a wrong depths within the description. And the unstable shales contaminate the cuttings, and those adjectives which are being added to the drill fluid can cause some contamination to the cutting samples. We will see some examples, I guess, in the coming slides for some of the alteration that can happen to the cutting samples because of the wrong choice of drilling fluids. So this is the master log. This is the header. This is the name of the well, the client, the rig name, the country, the coordinates. We have the data engineer, pressure engineer, the geological supervisor. All those names are being mentioned in the header, and this is the legend for the lithologies and the samples and symbols in the master log. So we have rate of penetration. It's how many meters per hour are being penetrating by the drill bit. We have the detectors, and we have, this is the lithology from the cutting, and this is the interpreted lithology from the logs. Both of them are put it together in the master log. This is the depth, and this is the gas chromatography. Those are actually the gas. If we have any gas that is penetrated the borehole during the drilling, we have a detector that can indicate the presence of those gases in the borehole. This is the description done by the geologist for the samples. So this is an example. Here is the lithology description from the cutting samples, and this description from the well logs. So as we see the difference and the variation between the well logs description and the cutting samples description. It is this description: transparent, translucent, and consolidated, very fine, mid-grain, abundant of mid-grain, minor, very fine grain, sub-rounded, well sorted quartz, and so on. So you will find the description, a detailed description of the cutting samples that are coming from each and specific depth. And those actually the oil shows those intervals that are contain hydrocarbon are represented by those black lines, which indicate that either the samples contain some indicator of hydrocarbon or some. Now this is another example of master log. In this example, there is a difference between the description of the cutting sample and the interpreted from the log. We can see that according to the cutting samples, the description was that there is anhydrite and shale, while when we come to the interpreted lithology, that there is salts and only this amount is the anhydrite and this amount is shale. So in this example, the reason for this variation in the interpretation was that the drill fluid was wrong. So the drill fluid caused the solubility of the salt. The salt was dissolved in the drill fluid, and it was not indicated by the geologist in the cutting sample. He didn't see any cutting samples of salt, but that was being able to absorb by the change in the salinity of the drill fluid. And as we said earlier, that the drill fluid is continuously monitored and observed to indicate such changes that can take place. And another factor that lead to this conclusion, in addition to the increase of salinity, there was an increase in rate of penetration. So that was a clear indicator that this salt is actually dissolved in the drill fluid, and it was absent in the cutting sample, but it was clear in the increase of the salinity of the drill fluid. Now the wellbore stability and mid-weight window. We talk about the mid-weight window and the drilling condition. So we have here various drilling condition, and as we said earlier, that the pore pressure, it's the formation pressure. If it's above the mid-weight window, that will lead to major kicks or blowouts. So the formation fluids will flow into the borehole. So our mid-weight has to be above the pore pressure, and at the same time it has to be less than fracture gradient. If the fracture gradient, if the mud window was above the fracture gradient that we can cause an induced fracture, and the drill fluid will flow into the borehole and cause what it called loss circulation. So the drill fluid will not come back to the surface, it will actually go through the formation within those fractures that was caused by the overpressured mudwet. So other than that, we have another parameter, which is wall bore collapse gradient, and this is actually the collapse gradient is the minimum mudwet that maintain the borehole stability. So above this parameter, we are in the safe drilling zone, so we will not face any formation damage, we will not face any kicks, we will not face any blowouts, and this parameter has always to be above the pore pressure or the formation pressure. So this is actually the typical or the best drilling condition in which the mudwet is above the collapse gradient and above same time above the pore pressure, while at the same time below the fracture gradient. Now, if our mudwet window was below the collapse gradient, and as we said, the collapse gradient is the minimum mudwet required to maintain the borehole stability. So if our mudwet is below the collapse gradient, that means we will have a wellbore stability problems. That means those kind of wellbore stability, for example, we will have shale swelling. The formation which are composed of shale will swell, and those loose formation will collapse into the borehole, and that can cause a serious problems, stacking of the drill bits and drill string in the borehole and so on. So this is a non-favorable condition for drilling. Sorry, in this condition, as I said earlier, that the wellbore collapse gradient has always to be above the pore pressure gradient, but there is some condition in which we prefer to drill where the collapse gradient is below the pore pressure. So in this, what does that mean is that we are allowing the formation fluids to flow into the borehole, and this is called the underbalance drilling, and it's mostly take place drilling during the exploration phase, because we want some gases, for example, from very tight formation to flow into the formation into the borehole in order to indicate those promising zones. Another case in which we prefer to drill under balance is in this case, when we are drilling under balance, we actually drilling under low pressure, so that will increase the rate of penetration, because the drill bit is now under low pressure and can drill more, and that will reduce the drilling time. Another thing is when we are drilling under low pressure, so we are not causing any formation damage. So we are not damaging the formation, we are not causing any fractures in the formation, and we are not pushing any fluids into the formation. And one of the main operations that take place after drilling is formation cleaning, which is the removing all drilling fluid that is penetrated in the formation, because it will, as we see earlier in the bridging, if the fluids are moving, solid particles will block the formation, causing the production problems. So if we are drilling under balance, we are the cleaning process of the formation will be easier. And something to mention is that in this case, this case can only happen in very intact and solid formation, because if the collapse gradient is below the pore pressure, what that means is that this formation is intact, solid, and able to support itself. So in this case only we can drill under balance. This is the last case in which we have our pore pressure gradient and the fracture gradient, but our wellbore collapse gradient is very close to the fracture gradient, and this case is on take place in mostly in carbonate or highly fractured reservoirs. So our drilling window is very tight and narrow, and we have to maintain our mud weight within this zone. It should not be above the fracture gradient that can cause induced fracture, and it cannot be below the collapse gradient that can cause wellbore stability problem. And this is actually can be maintained by a technique called managed pressure drilling, I guess. A managed pressure drilling in which through geomechanics you can calculate the wellbore collapse gradient and the fracture gradient, and maintain your mud weight window in between those two parameters. Now we are coming to wireline logging. We also covered this topic in previous year one, and logging is recording of the physical properties of the rock penetrated by the well. So as we are drilling, we are actually measuring those properties like porosity, permeability, and lithology of the subsurface formation. Logging can take place either during drilling or within drilling intervals, or after the drilling operation finished. Wireline loggings is actually a logging tool that is lowered to the boreholes through a cable within the drill rig, And this is an example of some of the logging tools. They are actually put in combination. You will find many tools attached together and to measure specific properties. As I said earlier, you are taking between drilling of episodes at the end of the drilling. Recently we have those techniques that can allow measurement during the drilling operation, which is called measuring while drilling or logging while drilling, and we will see the difference in coming slides. So this is the outcome of the wireline logging. It's the logging sheet. It's composed of 4 tracks. The first track contains the gamma ray, the SP, the caliper, and the bed size. And those mostly given the caliper given indicate of the borehole environment, the borehole conditions. The gamma ray and the SP can be used to give an indicator of the lithology and the permeable zone and unpermeable zone, and the bed size is the bed size to give us what is the diameter of the bed size, because this can be helpful with the caliper to indicate any variation in between those two. It's actually an indicator of alterations or changes in the borehole environment. The second track is the depth track. It can be in feet or meters. The third track is the resistivity track, and it's in logarithmic scale. Each tool have its own colors. For example, in this, the dashed black line is the caliper, the green is the gamma ray. So according to the scale of those two from here to here, we can divide those intervals accordingly, and we can read exactly what is the values. The same thing here in the resistivity, we have logarithmic scale. So according to each division of those, we can read the resistivity values. And the fourth track is the porosity track, which contain density, neutron, and solid. Actually, this is not the porosity track, but it's most of the time it's in the third track. So the presentation of the log data, we have this track 1 is the depth track, this is second track, this is the third track. So this is a logarithmic scale for the resistivity from 0 to 1, from 1 to 10, 10 to 100, and 100 to 1000. And this normally it ends up at 2000 at this point. The rest we just take the minimum and the maximum values, count how many units we have in between, divided by the units in the track, and we can find each block is actually equal to a specific amount. So this is another representation of the log. You can see clearly gamma ray in red, bit size, this one, the caliper, the black line, and the SP is in the blue. Regardless the variation in the, obviously each tool have its own scale, but the technique, as I said, it's the same. We find the minimum, the maximum divided by the number of units or blocks, and then we can find how the value of each plug, and then we can use it to read the value. For example, we have here 0 to 200, and we have 1, 2, 3, 4, 5. So each one of those is we divide 200 by 5, so each one is 40. So in this interval is the values of gamma ray in this zone is actually 40. In this zone is almost 80. The same thing if we come to SP, we have minus 160 to 40, and so that means until this is we have to add 40 to it, so it will be minus 120, minus 80, minus 40, and this is 0, and this is plus 40. So this value here is actually 0. Anything above this could be more. And the caliber is the same thing. We see that this is the bed size and this is the caliber, so we can see clearly that the caliber is reading more than the bed size. So the bed size is 0 to 30, and we have 5, so each one is 6, 12, 18. So the bed size is 18, while the caliber is reading more than 18. So we have a lot of, we can indicate that the borehole environment is very bad. We have a lot of washouts in those intervals here. Those are mostly washouts, and so on. So this is the main way to read a log. Now we come to the difference between measurement while drilling, logging while drilling, and wireline logging. So the difference between, we can categorize it into firstly into two groups: wireline logging and measurement while drilling and logging while drilling in that same second group. So this can represent logging while drilling and measurement while drilling, in which the logging tools or the measurement tools are actually attached to the drill bits. So as we are drilling, we are actually logging and measuring, while in wireline logging, after we finish with the drilling operation, we remove the drill string and we come up with the logging unit, and we lower the logging tool into the borehole, and we measure as we are going upwards. So we lower the tool to the total depth of the borehole, and then we measure as we are moving upward in wireline logging. While in those two operations, we actually measuring downward, and we are measuring as we are drilling. So it's a real-time measurement or real-time logging. Now between those two, the logging while drilling and measurement while drilling, there is also some differences. The differences are in what we are actually measuring. So in measurement while drilling, we are actually measuring inclination, azimuth, tool face, gamma ray, weight on bit, performance sensor. Those are sensors that are measuring the performance of the drilling operation, and the transmission of the data. Now in the term of transmission of the data, those two operations transmit data in either two ways: either through the drill fluid and electrical pulses through the drill fluid to the surface, or some of the tools contain a memory chip which can store those information and then can be retrieved. After it being retrieved to the surface, we took this chip and then we analyze those information. While in wireline, those information are actually transported through this cable to the surface. This is the difference. Now we come back to the measurement. As we said, measurement is actually related. Those measurements are actually related to the drill operation, the formation temperature, the formation pressure, and so on. While in logging, while drilling, we are actually measuring those physical properties related to the formation, like porosity, resistivity, lithology information, caliber for the borehole environment, and so on. So in conclusion, I will repeat this again. We have wireline logging, we have measurement and logging line drilling. The difference between those two is the way that the operation works. In wireline, it's through cable. In logging and measurement while drilling, it's through drill string itself. At the same time, in wireline logging, we are measuring those after the drill operation is finished, and we are lowering the tool through the cable to the bottom of the borehole, and we took this formation as we goes upward. While in this, the information are actually collected during the drilling operation. And the third thing is the way that those information are being transported is either through chips, memory chips, or through the drill fluid itself in the form of electrical pulses, where in wireline logging it's transferred through the cable itself. And between those two, the difference is in what we are actually measuring. Here we are measuring information related to the formation, while in this one we are measuring information related to the drilling operation. This is a conclusion for whatever I have said earlier. This is a demonstration for how the information are actually transported to the surface during the drilling operation in measurement or logging while drilling. So those pulses are actually, they are not moving in the through the drilling fluid which is flowing to the surface. It's actually moving through the drilling fluid which is inside the drill pipe. So most of the people will imagine that it goes with the mud fluid which is flowing in this interval in the annulus zone between the drill bit and the formation, while it's actually moving through the drill fluid in the drill string, and it goes in the form of electrical pulses which is received in the surface, and it's translated into a 0-1 parameter or language, or which is the language understood by the computer, and then translated in a form that can be understood by a human. This is also summarization for what actually we get from each equipment in the drill in the direction and drilling operation. And now some directional drilling scenarios. Why we go for directional drillings? We have some specific cases in which we are going for directional drilling. Some sidetracking. Maybe we have a borehole and we reach some interval in which we have a problem. Maybe the tool have stuck in this zone, so we don't want to abandon this borehole. We can go for sidetracking and continue drilling next to this interval. Another scenario is inaccessible location. We have a city in some place and we have some hydrocarbon accumulation below, so we go for directional drilling to reach this target. In salt domes, we cannot drill directly above the salt zone, so we go for sidetracking for directional drilling to reach this hydrocarbon accumulation below the salt dome. Another scenario is to avoid faulted zone. We have fault here because faults during drilling can cause a very serious problems for the drilling operation. So in order to avoid this fault, we go for directional drilling. Another thing is relief well. We have a well that have any problem like a blowout or something, and after shutting down this well, we want to continue producing from this interval, or in order to in some cases of blowout, when the blowout is uncontrollable, you cannot control the blowout or prevent it, so you go for sidetracking. For directional drilling, you drill another well that intersect with the original one, and then you start producing the hydrocarbon, and then this well will automatically stop. Platform or pads in which we have multiple hydrocarbon accumulations, and we need to drill multiple wells to reach each and every target, so we go for directional drilling. Drainage. In this scenario, we actually want to increase the area of production. Is mostly used for very thin reservoir, because we cannot drill vertically, so we go for horizontal drilling or directional drilling to increase the zone from which we can produce. Multilateral, in this scenario we are actually targeting multiple hydrocarbon accumulation from the same well. We have one specific well and we want to get hydrocarbon from multiple reservoirs through the same wells. So those are some scenarios in which we go for directional drilling. Now, cementing. We talk about cementing before, and we said that the borehole is actually drilled in section, and each section has a specific name: the conductor, the surface casing, intermediate casing, and the production casing. And those after drilling, each interval is actually being cased and cemented, and cementing is actually to prevent freshwater contamination of the freshwater zone, to prevent upper formation from caving in and sinking into the borehole. Isolate different zone, seal high pressure zones, and prevent fluid loss into the formation, and provide smooth internal borehole for installing production equipment. So in order to install production equipment, we need to finish the casing. This is a diagram show the different casing sizes: surface conductor and surface casing, intermediate, another intermediate, and the production casing. Each and have its specific diameter and specific depth. Now the completion is the next stage. After we done with the casing and cementing, we install our casing, we securely cemented this casing in the borehole. Now we come to the completion phase, in which now we are completing the borehole in order to start production of either oil and gas. And the completion type or the completion design depends on what we are actually producing. If we are producing gas, the completion is different from the completion of the oil producing well. Even if we have multi sections or multi reservoir above each other, if the completion will be different. Either if we want to produce the hydrocarbon from the both reservoirs at the same time, or we want to separate the production of one reservoir from the another. So we have which is called commingled completion. The completion design is depends on the profitability. It has to have a minimum operation cost over its life, flexibility to handle current and future problem. It has to be simple during installation and maintenance activity. So this is a completion equipment. It's to allow the flow of the hydrocarbon from the red one is the hydrocarbon. It's to flow through the completion equipment into the surface to the Christmas tree. And it also has to allow, as we said, intervention if we need to intervene or to maintain the borehole in the future operation. All those things has to be kept in mind during the design, the completion design. So the downhole emergency isolation in case of any emergency, to protect the casing, because this is the casing interval. It should prevent any hydrocarbon to flow in this interval that can cause damage to the casing. Permit downhole chemical injection. It should allow in the future, if we need to inject any chemicals in order, for example, to enhance the recovery of the hydrocarbon. So this completion design has to allow such operations to take place. Permit downhole measurement if we want to do any measurement in the future. So this completion design should allow such a process to happen. and isolate production zone. As we see here, this is the production zone, and it's totally isolated from the rest of the borehole, so we don't see any hydrocarbon that flow in the annulus between the completion equipment and the casing. Now we have two types of completion. We have an open hole completion, in which the formation is naturally produced. There is no casing in the interval, in this interval of production, while in the cased completion, there is actually a casing. In this case, we need to do a perforation when we generate some holes in the casing in order to allow the hydrocarbon to flow from the formation into the borehole. So we are actually perforating both the cement and the casing. This is how perforation takes place. After the casing and cementing, we are lowering the perforating gun, which is a tool that contains some guns that can release a high charge energy through the formation that can penetrate through the casing and cement and into the formation, and that allow the fluids from the formation to flow through those perforated intervals and through the borehole. This is the charges. Each is even the charges in the perforated gun are actually it's not randomly installed. It should be specific amounts, specific direction, and specific arrangement. Now we have in conventional drilling, after we install the production pipe and we perforate. Now we can normally start production naturally, but in unconventional scenarios, after this operation we go to the next step, which is called reservoir stimulation, in which we create, or fracking, in which we create fractures into the reservoir, very tight reservoir, to allow hydrocarbon to flow, or to stimulate hydrocarbons to flow to the formation. So we have to see a natural completion and unconventional exploration of tight reservoir. We actually go to the well stimulation. The Christmas tree is the last thing that is one of the things that installed in the top of the borehole, and it play a very important role because it's allow the production of hydrocarbon from the borehole. It goes from the borehole to production wing valve. This is the valve control the production. As we see here, the hydrocarbon goes through, and this to the through this tube to the area of collection or treatment. This is the kill wing. If we want to kill the borehole for any reason, we use this one. We have multiple valves. Each and every valve have specific job to do, and besides, it's also provide an access after the installation of the Christmas tree, the only way to access the borehole is through this Christmas tree. If we want to inject any chemicals, or if we want to kill the borehole, if we want to circulate anything, it has to be done through the borehole, and mostly it can be done through the operation of slick line, which is a very thin type of cable that allow the installation of any tools or even maintenance of the borehole in the future. It can be done through slick line or through the coil tubing. Sorry, it's called coil tubing. It can be done through the Christmas tree. The final last slide. After all this operation, the artificial lifting is the process in which hydrocarbon are pumped from the borehole to the surface. And we said earlier that any oil field goes through different stages of production. At the first stage or primary production stage, it can produce hydrocarbon naturally by the formation pressure, and after a while the formation pressure will drop, depending on whether it is water drive or gas drive formation, or either the formation pressure. With the time, all those mechanisms will drop, and we will see that the amount of hydrocarbon produced will reduce, and then we have to increase it somehow. So in the second stage, we go for artificial lifting, in which we use different type of pumps that can pump hydrocarbon from the formation into the surface. And even this process, it can operate for a specific time interval, and we reach some time in which even the artificial lifting is no longer effective, so we have to go for another processes that increase the amount of hydrocarbon, and that can be analyzed by the increase of water cut, because the variation in viscosity between hydrocarbon and water, allowing the flow of water, the water will flow more easier into the formation than hydrocarbon. So we will observe with the time that the amount of water produced with the hydrocarbon will keep increasing, either in the early stage of production or in the secondary production. So, and that will take us to the third stage of production, in which we go for IOR and EOR, enhanced oil recovery and improved oil recovery, in which we use some either water or steam or gas or polymers that is injected, for example, in some wall, which is borehole, which is called well bore, the injection well, and we produce through another well. So those are chemicals, gases or water or whatever we are pushing through the well bore is actually pushing hydrocarbons within the reservoir to be allowed to produce into another borehole. So by this we will be done with the introduction for the oil industry, and by this we hopefully have covered all the aspect or domains in oil industry in some details. Starting from next class, we will start with the formation evaluation, and reserve estimation and all those things. So thank you for the time, and see you soon.